Hello, I'm Cornelia Lyric.
And I'm Laura Parrish, and we're in Dr. Zobel's Chem 108 class, and this is our instructional video.
Our educational goal is to determine the amount of energy required to change the temperature of the substance given the specific heat of that substance.
Alright, so this is our experiment. We're actually going to set up a calorimeter with the stirring rod and a thermometer and its lid, as you can see here. We also have a 600 milliliter beaker filled 2/3 of the way with water and some boiling chips. We also have an unknown metal in a very large test tube here with a stopper on top, as you can see. And we have the hot plate going, and we're getting our water boiling now. So while we're getting the water boiling, we'll just explain to you how we're going to get to where we're going with this experiment. Heat is a form of energy that will pass spontaneously from an object at a high temperature to an object at a lower temperature. When heat energy flows into a substance, the temperature of that substance will increase. The quantity of heat energy, Q, required to cause a temperature change in any substance is equal to specific heat, S, of that particular substance times the mass, M, of the substance times the temperature change, delta T.
This is our equation that we have written up.
There you go. The specific heat can be considered to be the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius. In this case, we're using water. Amounts of heat energy are measured in either joules or calories. To raise the temperature of 1 gram of water by 1 degree Celsius, 4.184 joules of heat must be added to the water. The specific heat of water is therefore 4.184 joules per gram degree Celsius. The specific heat of a metal can readily be measured in a calorimeter. A calorimeter is a container with a known heat capacity. This is our calorimeter. When heating or cooling process in calorimeter occurs, the amount of energy or heat gained or lost in the process is absorbed by the calorimeter. This energy can be calculated from the equation if the calorimeter's change in temperature is measured, since its heat, capacity, and mass are already known. If one assumes that a negligible amount of heat escapes the insulated container of the calorimeter and there is negligible change in temperature of the container during the process, then all the energy released during the process of interest goes into the water. Since we know the heat capacity and the mass of the water using the calorimeter and can measure the temperature change of the water, then we can use the equation we showed you to calculate energy gained or lost by water.
Once again, here's the equation.
There it is. We will use a pre-weighed amount of a metal to heat some known temperature to some known temperature, then quickly transfer it into the calorimeter that contains a measured amount of water at a known temperature. Energy, or heat, flows from the metal into the water, and the two eventually equilibrates at some temperature between the initial temperatures of the water and metal. Assuming that no heat is lost from the calorimeter to the surroundings and that a negligible amount of energy is absorbed by the calorimeter walls, the amount of energy that flows from the heated metal as it cools is equal to the amount of energy absorbed by the water. In other words, the energy that the metal loses is equal to the energy that the water gains. So we're going to check our water, see if it's boiling. Maybe we could turn it up just a little tiny bit there. All right. And it looks to be just about boiling now. We're going to place the large test tube with our unknown pre-weighed metal in the boiling water and let it sit for 10 minutes so the temperature of the metal reaches the temperature of the boiling water. While the metal is getting hot, we can weigh the empty calorimeter without the stirring rod and the thermometer, but with the lid. We will then fill the calorimeter with 30 milliliters of water and weigh it again. The difference in mass between this weight and the weight of the calorimeter will be the mass of water in your equation. Now we will measure the initial temperature of the water in the calorimeter. So you want to hold hold the thermometer at an angle so that the bulb is completely underwater. And this temperature that you record will be the T initial in your equation. Alright, so as you can see, we've already inserted the stirrer and the thermometer into the calorimeter through the two holes, right? We just took the temperature. And now that our metal has been in the boiling water for at least 10 minutes, and it has reached 100 degrees Celsius, which is the temperature of the boiling water, they are at equilibrium. We'll take the test tube out of the beaker of boiling water. We'll remove the stopper, and then we'll, we'll take the lid off of our calorimeter, and we will pour the metal into the calorimeter, and we'll replace the cover and the stirring rod and the thermometer. And then we'll stir the water and the metal mixture as best we can with a glass stirrer. There you go. Now we'll take the temperature again, and the maximum temperature reached by the water in the calorimeter is the T final in your equation. Go ahead.
So as you can see, we have the specific heat, we have the mass of the water, and we have the change of temperature. Remember that the change of temperature includes the final temperature that you have got minus the initial temperature. Once you have got all those three parts of that equation, then you can find the heat of that energy.
And that concludes our instructional video. Thank you very much for watching.